Good afternoon and a pleasant afternoon to all of you, and welcome to our second Tech Talks, which is our enablement seminar series. So we'll be starting this series today. So this is something new that we're doing for our this year's enablement seminar. And of course, this year's session will bring various IT and software topics from the months of February to November. We're bringing you a total of 9 insightful sessions, of course, featuring 27 expert speakers that is packed into a 2-hour session. And of course, we hope you'll be looking forward to our next sessions for the following months. Okay, now before we start with our session, let me share with you our seminar rules. So, for a while, let me share my screen. Before I mention the seminar rules, can you input in the chat box if I'm clear? If my voice is clear? All right, thank you everyone. So here is our seminar rules. Okay, so participants, videos and microphones are disabled all throughout the seminar except during the Q&A portion where you can share your questions with our speakers. So of course there will be a Q&A question after each presentation or discussion of our speakers. So you can share your questions by raising your hand so we can unmute you, or you can share your questions in our Q&A chat box. And of course, the Secretariat will be recording this online Zoom seminar for documentation purposes. So, um, before we start with our session, of course, I would like to first introduce, sorry, sir, to introduce myself. So I am Camilo Campa, the Industry Relations Officer of PSIA, and I'm delighted to be your host for our second Enablement Seminar series here. So this session will talk about Apache Kafka. So, but before we go on to our speakers, let me please call on to the spotlight PSIA's Board of Director, Mr. Callen Legaspi, to give his message of support. So, Mr. Callen, the spotlight is.
Hi everyone. Good afternoon for the people in the Philippines and good morning to Daniel. Thank you so much for everyone attending, and in particular I want to thank Renz and Daniel for donating their time. It's especially difficult for Daniel because it's really early in the morning for him. But uh, again, this is all our events are always just community events. We didn't pay Renz or Daniel $1 million just to uh, um, present to us. So they're doing this for free. They're sharing their taking time out of their busy schedules to share their knowledge and experience with us. Um, and both of them are already are both of them working abroad. So Renz, I know personally, he worked at ONB for a couple of years. Now he's a very accomplished architect in Singapore. And Daniel, of course, he was highly recommended to me. He's accomplished speaker in the United States on various technology topics. Um, so Kafka, it's been critical for building scalable, fault-tolerant, and event-driven systems today. Today, um, we're we're always concerned about how to manage all the data that's being generated. There's just more and more data being generated from different sources, and we can't seem to be able to process them in fast enough pace. And Kafka is a solution for that. Whether we're working on IoT, AI, or many other applications. There's so many opportunities. There's so many requirements that we can apply Apache Kafka in. Um, and this is all part of uh, our commitment. So I've been working with PSI, serving uh, as with PSIA since um, 2008. Um, we've again, it's just community endeavor. We were This is part of our work on the capability side to enable Filipino developers to to gain global skills, right? To take on global skills. Um, and so I'm thankful for the opportunity to serve, um, to and for all the people that have been working hard to put these seminars together. So this year we decided instead of every quarter, we're doing enable seminars every month now. And I'd like to thank the secretariat who's been busy putting these things together. They're besides all the other activities of the PSIA, they're busy organizing these seminars as well. All right, so I'll turn it over back to the secretariat. Thanks everyone. Enjoy the seminar.
Thank you so much for your warm words of support, Sir Callan. So, without further ado, let me introduce to you our first speaker for this afternoon. So, our very first speaker here in this afternoon is Mr. Daniel Hinojosa, who is a programmer consultant, instructor, speaker, and author. He has also nearly 30 years of experience and work for private, educational, and government institutions. Sir Daniel loves JVM language like Java, Groovy, and Scala, but also works with non-JVM languages like Haskell, Ruby, Python, Lisp, C, and C++. So this afternoon, he will be discussing Kafka. Why is it important? So let us all welcome Sir Daniel Hinojosa.
Well, thank you very much. That was outstanding. Hopefully everyone can hear me okay. Can you hear me all right? All right. I think so. So I will let's go ahead and get started then. So we're going to be talking about Kafka, why it's important, why it continues to be important. And I'm going to start here just with the point. And the point here is that this is the essential data backplane for any kind of modern architecture is what's going on here. So with this, let's take a look at this particular diagram here. We have Kafka at again, the centerpiece of many architectures. So for something like retrieving information, this is about maintaining, keeping messages over the course of time. You have microservices over here, be it Spring, be it Go, or be it Quarkus, or Node, or any one of those that when messages get sent, they get sent over to Kafka. Kafka is essentially a buffer, and it is going to hold messages for retrieval by others. It is a way that we can implement EDA, which is called event-driven architecture. And with these events, whenever a particular system wants to state, hey, this is what occurred, then Kafka is a really great way to go about it. It is particularly fast. It's low latency. It's very high throughput. And that's one of the characteristics that we look for a particular messaging system. And so, yeah, we could bring things in from a particular microservice. These microservices can be called via REST or GraphQL or gRPC. We could also have, sockets and files that write over to Kafka. Okay. Now, what can we do with that? Messages will get posted here onto Kafka. Can we do something else with it? The answer is absolutely yes. So one of the things that we could do, and I think this is one of the more important factors of it, is that Kafka can either post over to a database, or we can get information from a database and post over to Kafka. This right here is a bidirectional arrow, meaning I can go from Kafka to a database or from a database to Kafka, okay? And this right here is going to be using something called Kafka Connect. And Kafka Connect is a way that we can communicate from a database over to a messaging system, in our case, Kafka, right? That's what we would be using. So if you think about it, let's say you have a classic setup of a web server and a database, and you don't want to, start unplugging things. You would like to use Kafka. One of the things that, you know, often people think about is like, now I got to tear the whole thing up. And the answer is no, you don't. So you could place into Kafka, have a Kafka connect to it. You can still have your, keep your connections for a while. So let's say, I have an Oracle database here, and let's say then that, I still have, my classic, my my classic web server right over here. I'm trying to draw a computer, by the way. Anyway, so that's a computer here connected to the database. Well, that's fine, right? That database can then still connect over to Kafka. Let's talk about some of the other arrows here. This one's a very important one right over here on the upper right-hand side. These are stream processors. The idea for a stream processor is the moment a message hits over here to Kafka, that's when I want to capture that information, do something with it. So in other words, as part of that stream process, let's retrieve that message the moment that it hits. Let's retrieve that message, do something with it, and we could do whatever we want with it. We could join it with other information. We can filter things out, and a whole lot more. But we want to do something with that message the moment that it appears. And whatever it is that we decide to do with it, let's post it over to a different topic. And there are different stream processors that we could use. Kafka has Kafka streams, but also like part of the Confluent stack. Confluent is the backing company behind Kafka. They have taken a large interest into Flink, and Flink is a stream processor as well. Both are kind of competitors, but I think Flink has definitely a little bit more power to it as far as querying capabilities go. But the choice is yours, and you can choose any one of these. There's Akka Streams, which is Scala and Java based, but the idea here is that, when something happens, we just take that information and we could tie it into Kafka or other data sources, same as Flink. And then there's Spark Streaming, structured or unstructured streaming processes that you can use. So again, the moment that a message hits in Kafka, I want to take that information, do something with it, and then post it somewhere. Kafka Streams is unique in that it's only topics that you interact with. So you always take from one topic and post it to another topic. I kind of like that, but that's the way that works. The others like Flink and Spark and Akka, you can take from one data source and post it to a database or whatever it is you want. In fact, it doesn't even have to use Kafka if you don't want to, at least for the Akka streams, Flink and Spark Stream. But then as time goes on, one of the things that you would like to do is you would like to aggregate it. And so there's Apache Pinot and there's a few other ones as well. And what these do are after the fact analysis, okay, or OLAP, online analytical processing, where you want to grab data and you want to do something with that data. That's where this comes in. Perhaps you want to train a model. And so this would be an aggregator that you can use. And in addition to everything, you could also have Spark for any kind of historical analysis. You could use Flink for something like that as well. What do I mean by historical analysis? Well, typically messages will go into Kafka for 1 week, 168 hours. And there they will be on that particular broker, okay, which is Kafka. Typically, though, for a lot of organizations, what they do is that, after things get processed, again, we're looking for real-time processing or near real-time processing. But after that message has already been processed, it gets typically deleted after 1 week. But you can make it 1 hour, 2 days, or 6 months, or you can keep it there infinity. But a lot of times that data will also be moved over here for a more permanent storage, so that way you can do a historic analysis on your data. Okay, and that's its use case, right? And that's how things are done. Now, also, why do we want to use Kafka? And again, why is it important? Well, you can create microservices and have different systems, and you could have RESTful endpoints on all of them, okay? And you could make the synchronous calls to say, I want to reach that system and get the information from it. The thing is, systems aren't always there. And maybe some other system is dependent on you. That makes the whole thing fragile. So how about instead that we have Kafka as the centerpiece? So microservices, again, can post to Kafka. Hey, this event just got generated, and here it is. Okay, and that's where we do a producer, or we can consume it. Consuming is, I'm interested in this information, and I want to do something about it. That's where the consumers will come in. So you have producers and consumers. And really that's the core of what Kafka will do for us. So oversimplified, we could have a producer, we could have a consumer, but we could also be both. So if I'm both, what does that mean? Well, if I'm both, I could be a consumer, do something with it, and then produce it. Consume, produce, consume, produce, consume, produce. And in the intermediary, let's change something or do something with it. That is called a stream. Consume and produce. So a consumer can be a producer as well, and you can combine them both. But rather than do that yourself, that's where you typically want to use Kafka Streams or Flink or any one of the stream processes. So Kafka is high throughput, millions of messages per second, replicated commit log, real-time data processing, and stream processing. Okay, we don't want to wait anymore. This is a different world. If someone posts a comment onto a social media outlet or like a YouTube or anything like that, the moment that comment hits, nobody wants to wait around forever. They have that demand for, quick visuals on your posts and your data and things like that. So how are messages produced? So messages are produced from that producer. That's the way that works in Kafka. We write to partitions is the way things work with Kafka. So we can have one topic. A topic is analogous to a database table. And that database table will have multiple partitions. Typically what you want to go with is you want to go with a number that has many multiples. So like 25 would be a multiple of 2, of 5, and maybe 30 would even be a better one, 6 and 5 and 10 and 3, right? Those have many multiples. And one of the reasons for that is that you want a nice distribution of your data across multiple partitions. But a partition is a subdivision of your data. This is by design, and one of the reasons is because we don't want all our data in one place. We want to make it fault tolerant. So a producer produces a message. A partition holds the messages. So we have 0, 1, 2, 3. Those are called offsets. Those numbers that you see there, they're kind of like addresses. And that's where messages are stored. So whenever I produce a message, for example, here it is, I'll produce a message, and right over here, it will be given an offset. Key characteristics. This is append only. Another key characteristic, this is immutable. I can't go in here and start to change that particular message. Okay. It's already written and it's here, right? And that's by design because we want to keep moving forward. Okay. 0, 1, 2, 3, 4. Data is temporary, so things will get removed as well. Remember, it's 168 hours or 1 week, after which they will get deleted. Now, if you wanted to keep that data around, that's where you typically move that into a much longer storage, like an S3 bucket or Snowflake or whatever, right? Or some other data store. But this is meant as that temporary storage unit for your data. But it's becoming more permanent now. A newspaper here in the US, New York Times, has it for infinity. And a lot of larger organizations, maybe even modern organizations, are thinking about having Kafka as that main storage long term. And so this one's there's a new feature within Kafka called tiered storage, in which it starts to use the cloud to back up this data. And it's always there, and it will recall it whenever it needs it, but it will start putting things on that tiered storage. So this may end up being more long-term than how we got started, okay? But let's say data did get deleted, and so this is the way it would look. We can't use the zero offset anymore. That's long gone, and we just keep moving forward. That's the way that works within Kafka. Data is temporary. We'll just continually add messages to it. And as we do so, we'll keep increasing that offset more and more and more. Okay. So how are messages consumed? Consumer is actually the harder part. Consumers will consume from the pub sub. Oftentimes people call this a queue, and they may be right very, very soon, but this is meant to be a pub sub, that messages are published and then they are subscribed. Let me do this slide again and this animation. Notice here that the messages stay. Okay. We're just merely getting a copy of those messages. Okay, that's a pub sub. I am subscribing from it. As a consumer, one of the things that I'll be doing, or either manually or automatically, it will be done, and that is managing the offset. So right over here, I just read messages 0, 1, and 2. So what I'm going to do, or what Kafka is going to do for me, is mark the offset, which is the next slot. So since I read 0, 1, and 2, the next slot that's going to be read is 3. And so a mark will be placed on here, and that's going to be that particular offset. Now, when more messages appear here, then I'll start to read from that one particular offset. Whatever I read from there, the offset will then get marked over towards the end, ready to process this again. I need this, or everybody needs this, because you don't want to reprocess messages over and over again. This is what will cause at least one semantic, in that you'll get the message at the other end at least once. You may get it one time, and you should probably get it one time, but you'll probably get it 2, 3, 4, or 5 times, if things go wrong. But we're aiming for one. It's called exactly one semantic. But you could read from the beginning. You could read from the end. You could read from whatever offset that you need to. So here's an example of reading from an end, or you can manage it yourself. So one of the things that could be done is within your microservice boundary, you could have your own storage. And once you have your own storage, you could ask it, hey, where was my offset last time? I wish to use the database for that, and here it is. So I could just say, I'm gonna read from that point onward. Now, how Kafka works as well is like this. I have multiple brokers. Here's broker 1, or I'm sorry, broker 0, broker 1, and broker 2. I am going to be posting a message. Where does it go? Well, here's the layout again. A small example. I have broker 0. This broker 0 has topic A. Remember, topics are like database tables. So here's topic A, partition 0. Here's B, 2. Here's C, 1. This is inside of broker 0, which is a machine, virtual or physical. Okay. Here's Kafka broker number 1, where I am housing A1, B0, C2. Okay. And here's broker number 2 with A2, B1, and C0. If I need to write to B1, it's going to be onto this broker. So you can see here, this is the way we scale things in Kafka. If I need to write to A2, that will come in over here. But if I need to write to C1, that will come in over here. If I need to write or read to B0, that will be over here. Now I'm now including the word read and write. So if I need to read or write to A1, that will communicate with this particular broker. And this is called sharding. And that's the purpose, or one of the many purposes for sharding, is that we have it distributed across multiple machines. And so if I need to read or write to those machines, one machine doesn't get all the attention. It gets nicely distributed. Now, just because of behavior and human beings and things like that, sometimes one will get more attention than the other. But over the course of time, things should even out. Okay. What we're also looking at here are what are called leader partitions. Okay. And because there are replica partitions that are used for backup. But Kafka communicates with what's called leader partitioning. So here's A2, and that's the thing that's the partition I'm going to be communicating with. So it's how we do our scaling. That's the important. So how does it really work with replication? So if I have replication for a topic, let's say I created a topic called stock trades, and I made it, 3 partitions with a replication factor of 3, then I have like 9 partitions. But 3 of those partitions are the leader partitions, the others are backup. And so on this particular image here, what I'm showing are the leaderships. B2 is a leader, C1 is a leader, A0 is a leader. I read and write to these partitions. These other ones I do not. I do not read or write to these ones. These are called replicas, and they're meant as backups to leaders that are housed in other brokers. Okay, so this is a backup, this is a backup, this is a backup. I'm using the chess pieces. So the queen piece that I'm showing here, those are the leader partitions, and those are the ones that Kafka will read and write to. Here's this one. Okay, I will read and write to B0, read and write to A1, and read and write to C2. And here's this one right over here. Okay. And so a message is just binary data. It's whatever you want to put into it. When I send a message over to this leader partition, it is analogous to a row or record. No special serialization as far as Kafka is concerned. The serialization is on you, the developer, because you want things to look a certain way. So if I say the message is a string, then that's up to me to consider it a string. Kafka does not. Kafka just considers things ones and zeros. Typically, though, a message a message will have the message part of it and also the key, or the value we call it. But the key drives where this message is going to go. That's the idea. Okay. And it's the only way that we get something done in order. So if I want order in a partition, then I'll use a key for that. So let's see how you take a look from the producer side, and let's get into a little bit more fine-grained detail there. So when I send messages over to that leader, I have the option to send that as a batch. Let's think about when you travel to work. And so you travel to work, you could take a car, you have a personal vehicle, you could take a moped, or you could get on the bus and you could take a public transit, or you can take the train. Okay. When you take your own moped, when you take your own car, that is a low latency. What's low latency about it? Well, I'm just, I'm leaving my house or I'm leaving my apartment and I'm getting on a vehicle that I own and I'm going, right? I don't have to wait for anybody, but I just go. But the thing about that is, you're only taking one person, and that's you, maybe 2 people, or maybe 3 or 4 if you have a larger car. But a bus or a train takes a whole lot more people. But you have a higher latency. You got to wait at the bus stop or you got to go to the train station. There's a waiting period for that. But what's great about that is you can put more people in it. You can transport more people effectively, and you kind of save on pollution and other things like that. Well, the same thing happens here. When you batch items together, you transport things efficiently over the wire. Now, you could have it low latency, which is once I have a message, send it, or I could batch things up to make it a higher throughput. And here's the important thing. How do they find their way to those leader partitions? Well, they know where everything is, and every batch knows where it's going. One of the things about a producer is this. When you program this and you say send, that send doesn't like magically appear in Kafka. There's a process, and that process is there's a buffer pool associated with it. Buffer pool is a memory set here where we can, set up the messages and they know where they're going. And in fact, there is a math formula that's used for these messages as we send them out. And that's called murmur2 by the number of partitions. Murmur2 is a hash. Okay. So here, let me come in over here and let's do the following here. So for an example, let me go to here. I'll go here, and I'm going to come in right over here. I'm going to go to this murmur hash Shore Labs here, and for this one, this is a hashing. We're just showing what a hash is. You have different kinds of hashes, and a hash is if I have a value like 25, or maybe I have a stock symbol like ORCL, that's going to generate a number. And it's going to be consistent, whether I do it on my machine or you do it on your machine, there's a consistent number on here. This is how blockchain works. And, this is the way that lots of databases work as well. It's called consistent hashing. So ORCL has a hash associated with it. Let's say in this case here, 398, etc. Let me go and copy that number. Let's bring it in here. Oh, there it was. I did this before. And so you can kind of see here the consistent hashing that ended up the same number. So this is for ORCL, which is an Oracle stock trade. Modulo number 25. Let's say I have 25 partitions for a particular topic. This will go to the 9th partition, I think. Taking a while. Oh, 19, yeah. So this will go to the 19th partition. That means that message is going to go always there. So I should expect all oracles to be there, okay? If I had, let's say Microsoft, for example, right? I will capture that number, bring that one in, and hit a run on there. And that will go to the 0th partition. So I should expect all of Microsoft's stocks to go to that particular partition. So if I'm doing a group by Microsoft's, then I can get all the information that I need here. Okay. And that's how that Kafka works. And that's how it distributes items. It uses that particular formula. Okay. Murmur2, modulo, number of partitions. We can also have acknowledgements as well from the producer side. Controls how many partition replicas must receive the record before the write is considered a success. So not all messages are the same. If I have a temperature reading from a sensor and I know I'm going to get a new one, if a message goes missing, I don't care, right? Some messages you shouldn't have to care about, but some you definitely do. So if you don't care of, missing some messages, just, make Axe 0. The benefit and the payoff that you get from it is that it's low latency. And if you think about it, like from a, postal carrier, you send mail to somebody, if it's an important thing, you may, want to pay extra postage so that way you get a return receipt or something like that, right? There's more involved to it. People have to do work in order to ensure that that message gets there safely. But if you don't care, right, maybe it's just a, letter to someone that you don't even know, or even, maybe you're writing to a company or something like that. If they get it, fine, who cares? But if it's your grandma or, your aunt or whatever, and, you want to make sure that that's important. So you'll take extra steps to ensure that safety. Same thing happens here with Kafka. If you don't care, then make it 0 and it goes out faster. Or you can make it 1. When you make it 1, then what this will do is that the leader partition, which we talked about, will send a kind of a receipt called an acknowledgement back saying, I got it, it's safe. Go ahead and remove it from your buffer. Remember, your producer has this buffer pool here where it gets prepped and the calculation is made before we send that out. Okay? And we have axe all, which is the ultimate safety, but also the higher latency, meaning it's going to take a while. Not a long, long time. Right? It's still reasonable, but it's not going to be super quick. So all replicas must acknowledge. So it goes to the leader, then the replicas will retrieve it, and then they'll send an acknowledgement to the leader, and the leader will send an acknowledgement back. Okay, let's take a look at a producer and how that looks. I'm going to be using Java. You could use any different language, and there are ways that you can write it in Python and C# or whatever. Java is typically the typical way that you program for Java. It's kind of like the de facto language, I guess. So here it is. And what I'm going to have here is I'm going to have a Bootstrap server. This is going to be whatever the address is. So this will go to typically 9092 is the port, and that's where I have a single broker. I have here a string serializer and an integer serializer. String is going to be the key here, so I'll need a serializer for that. Serializer is I have a Java object, and I want to make that into ones and zeros that Kafka can handle. And then here's the integer, and I'm going to keep this rather simple. Here is a producer. Okay. I'm going to instantiate it, and I'm going to give it the properties. Easy, right? On here, I'll come back to this one. But what I'm going to do is I'm going to craft a message. And what I'm doing with this one is I'm going to use a US state on here for the key. And what I'm going to do is I'm going to create an amount randomly between 50 and 100,000. And what I'm going to do is I'm going to create a record. And here's where I create a record. New producer record. Here's where the topic is going to be. Here's the key. And here's the value associated with that. Then finally here, I will do a send. Now this right over here is how I'm going to handle the situation if something either goes wrong or it's successful. If it's successful, I'll grab the metadata. If it is not successful, then I will trap the exception. And really that's all there is to it. So what I'm going to do is I'm going to come in right over here. This is called my orders. I'm going to go ahead and copy that. And let's see, what I'm going to do is I'm going to share part of my screen instead. Stand by. There we go. And what I'm going to do is I'm going to come in over here and I'm going to go to this control center here and go to topics. And I have something here called my orders already, but I'm going to delete that topic here. My underscore orders. Let me go and continue that. I don't think I have anything running. I guess I do have something running. What do I have running? I have something, I have a mystery running here. Let's see. But I think it's fine because what I'm going to do, I don't even think I need the underscore one. I'm going to create another one called my dash orders. I don't know what's running to where the other one's getting filled. So, but I'll go to do this one and I'll create with defaults here. What I'm going to do here is I'm going to do 3 partitions on this one. And that'll be important here. 3 is not a great number because that doesn't have multiples, but it's good for a demonstration. And here's where the messages will occur. And what I'll do is I'll go ahead and run this. And yeah, let's see what happens here. Oh, interesting. Let's see here. Let's try one more time. See if that was a fluke of there. I guess it wasn't. Yeah, let's come in here. And if that doesn't work, let's go ahead and come in here. And then I'll just run it from the command line. Yeah, there it is. Let's do exec java -d exec.main class is equal to com next, and then my producer. All right. Not sure why it's not running on my IntelliJ, but let's give that a try. And there we go. All right. So one of the things that you'll notice here is Arkansas, the state of Arkansas, 31,041 went to partition number 2. Okay. A new message will be coming up here soon, maybe. It should. Within 30 seconds, I should end up with another message. Might be taking a little bit of time here, but there we go. So here I have Connecticut, 77,916, and this one went to partition 0. What this means is that I should always, always, always find Arkansas or AR in partition number 2. I should always find Connecticut going into partition 0. And here's New Mexico, that's where I live. This one's going into partition number 2. Okay? And so you see that distribution. That's how a producer works. Okay? Let's wait for one more here on this side. And then we'll jump into the consumer and see how a consumer works. There it is. There's Georgia, and that's going to partition 0. I'm going to let this run for a bit, and let's take a look at how a consumer will work. Consumers are a little bit harder, though. Consumers have to be done as a particular group. And so, for example, here, I have one consumer, and this is not a good scenario to where I have multiple partitions and I have one consumer. This is, you've seen it before in stores and other places to where there's only one person on the counter helping everyone. And, it's tough, right? Or you go to a restaurant and, at that particular restaurant, there's only like 1 or 2 people working and everyone's there. That's an unfortunate situation. We don't want that to happen with our data. So what we do is we will use a consumer group. Consumer group is multiple consumers. Okay. Here, let me do it this way so that we can just see the slides here. Okay. Multiple consumers, they work together to get something done. Okay. If we have a single consumer, that will never catch up, particularly when there's large amounts of data. So let's break things up. That's the idea here. Okay. One partition would go to many multiple consumers here. So Kafka's goal is to use different consumers to process the data. And here's the thing. It's always cheaper to produce data than it is to consume it, right? Like even me giving this talk right now, I'm easily talking about Kafka. I've done it many times before, and I can easily convey the information. And you're probably interested, and you're like, oh, I'm going to do some Kafka applications myself. But then when you start to do it for the first time, it's not going to be fast for you, right? You got to have to like go through the motion, make sure everything compiles and things like that. So things are a little bit harder. Even basic communication, if I say write something down on a piece of paper, right? Me talking, that's easy. You writing it down, that's harder, right? And so consumers are always tasked with the harder work. It's going to be, and it's going to take a lot longer to do something with those messages. One of the rules you should know, it's one thread per consumer. Producers are multi-threaded, but consumers are not. So when you design these applications, just make sure that you know that, okay? And I'll actually stop you. So one of the things, again, from a consumer, I want to manage the offsets, okay? Meaning if I read from 0, 1, 2, I'm going to mark 3 as the next place that I'm going to read from. Then when I loop back around, I'm going to start from that offset. Read, 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 mark the offset. Read, 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 mark the offset. In fact, I'm reading in as batches is the way the consumer works. Consumers undergo rebalancing is the way that works. So this is a fault tolerance thing. If something fails, we got to keep going. And in fact, I usually say that, implementing Kafka at your company is not necessarily a cheap thing. You're paying for something though. You're paying for that fault tolerance. And that's a key component to all this. Because if something goes down, we got to keep moving. And that means you're going to have, systems continually running to ensure that that's going to work. Okay. So when a consumer goes down, we'll do a rebalance. Although unavoidable, this will lose state. So if you're managing state, be careful. So what do I mean by that? Let's say I am going to be calculating the average price per state. That's a state. I mean state like in the US state. But if I'm going to be calculating the price per state, I'm going to have to manage the state somewhere. Okay, New Mexico has 3, New York has 20, Nebraska has 5, etc. I need to write it somewhere. So I'm going to take this piece of paper and that's where I'm going to write it down. But state is a problematic thing. It's a good thing and it's a necessary thing, but it's a problematic thing when it comes to fault tolerance. So consumers will go down, right? If anyone's done any Kubernetes deployments, you know this, uh, that things fail all the time for different reasons. And so when a consumer goes down, we still need to keep processing. So a rebalance would be, given the consumers that I have, I'm going to route that elsewhere. So the way consumers work is using something called heartbeats. And heartbeats are the way consumers saying, I'm still alive, I'm still alive, I'm still alive, I'm still alive, and I'm still going strong. And unless you don't hear from me anymore, then go ahead and do a rebalance for that. So that's how things occur at those regular intervals. And they are sent to a particular broker. Now, how this works is I'm going to have something called a group name, marketing, sales, whatever that group name is. Given that particular group name, it's going to have a dedicated broker or server that will be its champion, essentially. And that particular server will track the health of the consumers. It's called a group coordinator. They are a heartbeat is sent when a consumer polls and consumes records. And so it continually sends that heartbeat out. We could leave a group and say consumer close. At that time, the group coordinator will be told, I'm out, going to figure out who gets what. And that's where that group coordinator will come in. And then, of course, a rebalance will then take place. Let's take a look at this one. I think this one will be valuable for many of you because you get to see how that fault tolerance works. Okay, let's take a look at that. All right, let me just change the screen share here. And here we go. All right, excellent. And it looks like I'll have to use the the command line. So anyway, my producer's been rolling here under my dash orders here. So looking pretty good. And yeah, let's take a look here. Just yeah, I guess I'll just do all terminal today. And that's fine. All right, let me go ahead and open up the consumer. Well, let's take a look at the consumer code and see what that's all about. Here's the consumer code. Couple of things. One is the Bootstrap server config. And then this one over here is the group ID. That's different. So whenever you write a consumer, you set up a group ID. That's what that refers to here. Then I have the deserializers. When we took a look at the producer side, the producer side had right over here, the producer had serializers. But as far as the consumer goes, the consumer has deserializers, which should make sense. Deserializers is give me the ones and zeros, and I'll reconstitute it into a string or an integer. Okay. So this one right here is where do I want to read from as a consumer? Do I want to start at the beginning? I will, right? That's the earliest here. If I don't want to, I'll make that one the latest. Okay. Now this one over here, this one is I wish to enable, disable auto commit, and I will commit my offsets. But let's take a look at the core items here for this. The core item for a consumer is this method here called poll. Pull is, hey, get me some new stuff. Do you have anything for me? Do you have anything for me? Do you have anything for me? Right? It continually asks that. And I continually ask that because I have a while here. So I'm going to continually ask, hey, do you have something for me to process? Do you have something for me to process, etc. So that's what that pull is. And I'm going to pull every 500 milliseconds. So let's say there's nothing for me. Do you have something for me? No. Oh. So in that case, this records right over here will be empty. And if that's empty, I'm not going to do anything with this for loop. And I will just continue on with my while loop, where I will wait again. Now, let's say there are two messages now. If there are two messages waiting for me, then this consumer records is going to be a group of two messages. This for loop here, I'll process these messages however I see fit. And that's it, right? Keep going, keep going, keep going. Right over here, I'm going to commit, after I'm done with a batch of messages, I'm going to commit this offset, saying, I've processed these messages, give me some more. And that's the way a consumer works, okay? When we shut down, I will go to commit, all the offsets that I've processed up to this point. And let me just add a warning in here. Private, let's say what I wanted to do is I wanted to have a count by state. Okay, let's say I create something like this as a member variable. I'm going to put in here, I'll go ahead and make a strong opinion. Do not do this. Super sad face, all right? And why? This is state that we're dealing with. So if I were doing a count, for example, like every time I process a record, and I do, count, put, or whatever I called it, and I put the record and I put the count on here, that's a cheap way to go about it, and it's also the wrong way to go about it. And that's why I put do not do this. And the reason is the consumer goes down. What happens to this state here? Gone. It's gone. Right? And so this is an irresponsible way to go about doing that. Don't do it that way. The better way, use a stream for that. And I'll show you a stream coming up. Okay. Let's run this consumer then. Here, let's give it a try here. It's probably going to have that error mess. Oh, no, that worked. Oh, surprisingly. I don't know why the producer didn't work. But you know what? I think, let's see. Yeah, my orders. Yep. Okay, that's working. Surprised. Oh, well. The producer didn't, but the consumer did. But anyways, you saw what's happening here. And take a look at what this consumer is reading here. This one's reading partition 2. It's reading a lot of partition 2, but it's also reading partition 0. And I think it's reading partition, there should be plenty of partition 1s here as well. There's a lot of zeros. Again, 3 wasn't probably the greatest number, but yeah, here's 1. So this one consumer is processing partition 0, partition 1, and partition 2. What I'm going to do is I'm going to run this a second time. Hopefully I can. Oh, it's not allowed to run in parallel. So why don't I do this? I'll stop that consumer and I'll go about it this way. Maybe the command line was better. So this one here, this one is the producer. I'll go ahead and call it that. There we go. There's the producer. And this one in here, I will run this one here as consumer 0. How about that? That way we could see it. And let me go ahead and run that one. And here we go. I'm going to call this one my consumer. There we go. Let's run the consumer here. So this is the first consumer on here. And what this should be doing is that this should be processing all of them. Okay. And what I'm going to do, and there it is. As you can see here, it's processing all of them. But what I'm going to do is I'm going to run it twice and 3 times and 4 times. Remember, I have 3 partitions, but here's the second consumer. Here we go. You'll see right here, this one says, I am reading partition 0 and 1. This original consumer lost it, all of them, which is fine. That's the way it's supposed to work. Let's see, where was that? There it is. You see here, partitions revoked 0, 1, and 2. But what we gained over here is just 2. So this consumer is just reading 2. This one is reading both 0 and 1, as we see that over here. Okay. Now I'm going to run it another time. So this, I'll call this one consumer 1. Okay. And I'm going to run it a third time here. And I'm going to rename this one consumer 2. Bingo. So now we have this wonderful situation now where I have one consumer per one partition. This is reading 0. This one is reading 1. See that right there. And this one over here is reading 2. Now I know you're interested. I can feel it. What happens if I run it a fourth time? I have 3 partitions, but what happens if I read it a fourth time? In this case, this one stole partition 1 from somebody else. So let's see who it stole it from. This one has 0. This one has 2. And this one, I think, lost it. Yeah, it's unemployed. So no more assignment on that. Okay. But what's cool about this is, if I control C that one and I take that one down, take a look at what this consumer is going to do. Here's the rebalance in action. And here we go. Partition assigned. Uh-oh. It usually takes quicker than this. I'm not sure why this is taking too long here. But inevitably, what this should be doing is that this should start to get reassigned here. Watch, when I'm not looking at it, that's when it'll get its act together. Or did I not? I thought I killed the other one. I should have. But what should happen is, ooh, kind of interesting here. I didn't realize IntelliJ had a Kafka here. Wow, I learned something every day. But yeah, there it goes. Oh my gosh, finally. That took forever. But we see over here that this has my orders 2, my orders 1, and 0. That's what a rebalance is. So if something fails, that's fine. Let it fail. The others will take over. Okay. So those are the consumers, and that's the way a consumer works. For a particular topic, we can have compaction for a particular topic. What is compaction? Compaction is, let's shrink the contents of, give me a second here. Yeah, I think you could see that. And you should be able to see my slide here. In fact, let me do this so that we can just focus on this slide. So on compaction, the idea for compaction is we shrink the contents of the table. Or not of the table, of the topic. I saw a table there. That's why I said table. But let's discuss, why did I say the word table? So topics can be compacted, and these are particular for topics that you consider a table. Now I'm going to bring in this word table. Why am I bringing up a table in this scenario here? Okay. Well, here's what compaction does without using the word table. Let's skip that word for now. Let's say I have these messages in here. And let's say in this case that, there are multiple keys for each one of these messages. Okay. Let's say these are employee records. Okay. Let's say Camille and Renz. These are the employee records. So, when Camille was hired, here's that original record. It's just an example here, okay? But let's say Camille got a raise, okay, and has a different salary. Well, you can't edit in place, right? This is immutable, and this is append only. And if this topic here is representing employees, for example, that's more of a table. Another word we use is change log. And that means that we are implementing a change. We're implementing a change, we're implementing a change, we're implementing an overriding change. So let's use Camille as an example here. Camille got hired. Camille has a different salary now. And since Camille has a different salary, let's say Camille's now living in a different address. Things change with Camille, as with everyone else, right? And right over here, let's say Camille's title had changed. Well, this is Camille's latest record, right? And let's say Renz, here's where Renz was hired. And let's say Renz over here, Renz got a change in salary, okay? People progress and situations progress within a particular company. Question to you then is, do you care about the past? Here's Camille's current situation, current salary, current address, everything, okay? That's the latest record. This is best represents Camille today, not the older records. Do I want to expunge these records? Up to you. But there's value in that I don't want to hold that information. I just want the current information. So I could do a compaction. And compaction is going to keep of course, the offset and the message itself, and it's going to expunge all the older records based on the key. And here's Renz right over here. That's a compaction. Okay. Perfect for tables. Now, what's a table and what's the alternative? Well, the alternative is called a stream, and that's the way we call it. So discrete business events that are happening is a stream. Things like employees, that's a table. And so when we process data, that's how we perceive it. And that's what we actually call it. Now, during compaction, more records get added, right? Camille goes through changes, Renz goes through changes, Halen goes through changes, et cetera, et cetera, et cetera, right? Every employee goes through a set of changes. And so these are the updates. Kafka will start compacting by default when 50% of the topic contains dirty records. Dirty records are new records that were added, and we'll do another compaction. So essentially, your topic is going to go like this, right? It's going to increase, it's going to shrink, increase and shrink, increase and shrink, increase and shrink. Because that's the kind of data that it is. And now this sets us up for streaming. Nice. Okay. So we have our producers, we have our consumers, and now we can talk about streaming. This is the power of it all, right? I want to process this data. And I don't want any long-term ETLs. I want short-term ETLs. You may have heard that term ETL before, and you may have not. ETL stands for extract, transform, load. Extract, transform, load. Take something out, do something with it, and then putting it somewhere else. And that's essentially what streaming is, except whenever a message arrives. For a long time, and still happening today, companies are doing long-term ETLs at the end of the week, at the end of the month, at the end of the quarter to process data. We don't want to do that anymore. We want to do things real time. The moment something changes, the moment a message hits Kafka, let's react to it really quick and do something with it. And the analogy here is very much like air ducts and water pipes and electricity circuits. The notion of a streaming is everywhere, and the same occurs with data. So we want to process our data. We have an endless supply of data. We want to replay it if we care to, and we want to do something with it. Maybe we want to detect fraud. Hey, my credit card has been run in 3 different countries in the last 3 minutes. Something should be flagged, and I need to know about it right now. If I did a long-term ETL and I didn't know about it at the end of the quarter, that's a problem. High-end sales detection. Someone spent a large amount of money on my company. I want to make sure they're going to be taken care of. Internet of Things, right? Your cars are data emitters now, and for good and bad. I'll stick to the good stuff. Like modern cars now tell you if you've been in an accident. That's wonderful, right? And so they can locate you, and it knows when your car's been in an accident, and they can communicate with you right away. Those are kind of nice things to have in a car. That's an Internet of Thing, and so those kind of things you want to react to immediately. Okay. But sometimes we'll need an aggregator, and that's where we have counting and grouping. Remember when I talked about the consumer, I said, don't do this. This will handle the state better. So how does a stream work? Well, a stream works very much like this. It is a consumer producer. And in fact, we are going to be using a consumer group just like before. We're going to call it an application ID instead of a group ID like before. But the idea is I want to extract from one topic and put it into another. The way a stream works is like this. I'm going to consume some messages. That's the extract. I'm going to transform it. So I'm going to use the color orange here to represent that transformation. And I'm going to post this onto a different topic. And maybe they'll have different destinations because of that. Really, that's what a stream is. Okay. And we could do a lot of things with this stream. We could filter it. So one of the things that we could do with a filtering is we could detect high-end orders. If I have an order from New York, great. But it doesn't meet my threshold of 10,000. So I'm not even going to consider it. But if I have someone coming from Ohio that is greater than 10,000, then go in and put that into that new topic. But I could even do complex things like aggregations. Let's take a look at this one. Let's say I have these orders in here. And what I want to do is I want to do a group by. So here's the state of Ohio, group by the state, and then I have this value here. Now, let's say what I want is a cumulative total by state. So what I have here is I have Ohio and 100. Here it is right over here. Ohio 100, Ohio 100. This is the group by table. This is the aggregate table. So given this, then, I'm going to create a orange message here to represent a new message. And this will be the current running total. Here's New York 20. Those are the elements. And here's the aggregate. Now the current running total for New York is 20. Okay, so far no big surprises. But how about this one? New York 60. Group by state or group by key, New York. Now I'm going to add 60 to this current running total. That's now 80. I'm going to create a message called 80 because that's the new total. And I'm going to post that over to a new topic. That's how aggregations work. And so I'll have a new topic with a new set of partitions, and this is the way it looks. Now, the question is, do I care about the old information? No, I absolutely don't, right? I could make an argument for the employees example that maybe I want to keep employees' older records. There's a good argument for that. But for this one, for account, nah, there's no reason for that. I know previously that there was a count of 1. I don't need to keep that information around. So I'm definitely going to compact it. Okay. Because I'm just maintaining that order. Now, we're in a situation here that we are aggregating, and aggregation needs a state. You've probably been through those turnstiles before where they have the little bars and you walk right through it. That's maintaining the state, right? Same sort of thing as like if I have a notebook and I'm watching people go by and I'm, taking count of them. That state has an ephemeral storage. It's called ephemeral storage, means it's attached to it. So every state processor has a database attached to it. And what we could do is we could back that up into a topic. said you got to be careful with that state, and that's where things get complicated. So when I consume and produce, this is one machine here, this is another machine here. Each stream process that we are running here has a consumer producer and a state store. So given this then, I am consuming, and if I'm updating the state, I'll update the state, right? And there it is, I updated that state. And then here's my producer here, whatever it is that I want to do, and I will post that over to a topic. Variable storage means that this state store is a part of the stream processor. And this state store is also going to get backed up into a topic. So a lot of powerful things that you could do with this as well, and that would be like windowing. So one of the cool things about windowing is something like this. This is a grouping, this is an aggregation. When certain elements fall within this particular window, this is called a tumble window because it's a 5-minute window with a 5-minute hop. Okay. And here's how that looks. 5-minute window, 5-minute hop. This was a hopping window where you have a different size of window and a different size of hop, different size of hop, different size of hop. Okay. Pretty cool. Notice the hop is different. It's a little bit smaller. And then here's the session window. Session window looks for inactivity. Let me run this again. As long as there's information, I'll make a window out of it. That's probably the best way I could say it. If there's no information, I'll set up a session window with a inactivity time. Let's say the inactivity time is 5 minutes. I don't see any more elements, so let me go and make that a window. I'm going to start to consume again. I'll wait 5 minutes. Let's say I waited 2 minutes and I see some more information, so I'll just go to make that a part of my window. Then let's say I'm going to wait 5 minutes, and let's say this one's just barely late. I'm going to make that a window and continue on there. So this captures bursts of information. Okay, and that's the way we could go about it. So that way you could analyze that information. Okay, wonderful. Let's take a look at a stream. So on this one then, I have this stream here. And what I'm going to be doing is I'm going to be creating a couple of other items here. But this is what a stream will do. A stream will take in from one topic and post to another. Okay. Now, it's an AI world now. And what Renz is going to talk to you about is like, where does AI fit into all of this? And streaming is going to be one of those key components in there. And I'll let Renz give you the details on that. But the idea for calling AI or doing any kind of transformation is streaming. So either in the case of a regular stream like this, or KSQLDB, or Flink, any one of those you can call ML as well. Because really that's what, extract, transform, do something with it, and load it somewhere else. What's a transformation mean? Well, transformation could be, let me call an AI or something like that, or, your own business transformations. That's the whole idea here. Okay. So key value Saturday. This is Saturday stands for serializer, deserializer. So here's the default here. I'm going to attach to this my orders that I've been producing on all this time. And I have the following, which is get me information from here. And if it's equal to the state of California, let's post this to a topic called California state orders. And I'll do a peek, and with a for each, I'll show that information here as well. Okay. And let's see here. Oh, sorry. Yeah. Thank you. Thank you. Thank you. Thank you. I'll change the screen here. All right, good. All right, let me do that one again. Sorry about that. So I have the application ID. Here it is. And here's the California state orders that I was referring to. I don't think I need these two. I think I added them a little bit later. So that one kind of stunned me there. But anyways, yes. So for my orders here, I'm going to go to California state orders if it is coming from California. And here's this one. I'm going to have a stream group by key. I'm going to take a count for that. And I'm going to dump this over to state orders count. This is a branch. So things are coming into my orders. On one branch, I want to do a filter based on California orders. And on this one over here, I want to do a group by. And as part of that group by, I want to do a count. So I want to do that count by state. This is the better way to go about it, or one of the better ways to go about it. Again, you have options. You can go with Flink. You could go with any of the other streaming utilities for that. Okay. So here I'm going to create an application. I'll just leave that part out. This is just creating the Kafka streams, and I will have a shutdown hook associated with that. So let me go ahead and run this one process here. And there it goes. And one of the things that we can see from this is the following. Let me come in here over to the broker, and let me open up a terminal so that way we could see what's going on here. Okay. And I have a little cheat sheet here. I have a cheat sheet because I knew it'd be like 3 in the morning, and my brain wouldn't be quite that sharp. Okay. And here it is. So what I'm going to do on this one is I'm going to take a look at California state orders. Let's take a look at what this has here. Great. I'm surprised I only have 2 orders, but here it is. So this shows here 2 California orders has been processed. That's what's inside of this topic called California state orders. Let's run this one here. This one is, let's take a look at the state orders count. Remember what this one was. Do a group by state and then do a count of that state. And now I have this topic right over here. Let's go and run that. And here we go. Now, this is a running process that we see here. Okay, this is always running. So here's Massachusetts 3. I think I'm still running my producer. There it is. Yeah, two just came in right now. Oh, in fact, beautiful. Look at, I was fortunate on this one. I see that previously Maine was at 2, but now it's at 3. So this is currently running a total on, the number of orders that I have through state. Beautiful, beautiful, beautiful. Okay. So a lot of great stuff there when it comes to a stream. So KSQL DB is built on streams that I just showed you here, except it uses a SQL-like syntax. Okay. So it's still the same thing. It's still a stream, just SQL. That's it. Fault tolerant, scalable, just like streaming, except you get to express yourself using SQL. You could do filtering, transformations, aggregations, joins, windowing, so much more. The idea for KSQL DB is this. You have a CLI that you can work with, and you have a KSQL DB server. Okay. So with that, you can query your data from that. Okay. There are different modes that you can run with this called headless and CLI. CLI is interactive. Headless is I want to deploy into production, and I don't want anyone to mess around with it. Okay, that's the idea there. In order to use this, though, you would typically need to do the following. Make sure your data has parts to it. Make sure your value is like a JSON, for example, or an Avro or a protobuf. You need structure in your values because you definitely want to query it. Okay? I'll show you an example of that. So you could write your own stream process in the raw using producer and consumer APIs that I showed you. You could also use Kafka streams, or you could use KSQL DB in order to do it. So you'll start in CLI mode, and what you could do is just start to run SQL commands against it. Okay. Here's how you start in headless mode. Now, let me just show like just a few of the slides here, just because I do have a lot of slides, and I should be wrapping up here soon. But let me just show you. Some examples here. Stand by. All right, there we go. Okay, so here's an example of a query. Select star from page views, where row time is greater than a certain element, or a certain time, and less than or equal to another certain time. This is called a pull query, which is just get me the information, right? And that's the query. It's not going to another topic. That's what we mean by non-persistent. But a push query is one where you call emit changes. So this looks very much like SQL, but it has an emit changes element to it. And then here's a persistent query. And this is the one I wanted to focus on. And you can kind of gather what this does here. This one says create table, but we could say create stream. You have two choices here, table or stream. Remember, table represents like the employee table that I was telling you about, where every update supersedes the previous one. That's what we're referring to here. And so what we're doing on this is the following. Get me the user ID, the gender ID, and the region ID from users, where gender is equal to female, and emit changes. Okay. And that makes a persistent query. Persistent in that we're going to end up with a topic called users female. Great. So I could take information from one topic, run this persistent query, and whatever the results are, that gets posted into a topic called users female. So if you don't want to run this functional style programming like with the Kafka streams, you don't have to. You have this KSQL DB. But this isn't the only game in town, and so Confluent, the backing company, is putting a lot of effort also into Flink as well. Flink also has a SQL. If you're into Spark, Spark also has a SQL as well. Okay. And for that AI integration, Renz is going to have a talk right after mine on how to do that. Okay, and talk to you about Kafka and AI integration. Here's a really big one here as an example. Create stream, page views transformed with these particular timestamps here. Select the following from page views, partition by, and emit changes. What the heck is all this? This is a big query here. Really what this is, and it's not too bad here, but what this is right over here is the following. Create stream, page views transformed. I'm going to end up with a topic called page views transformed. This is what the topic is going to look like. Value format is JSON, 5 partitions, and a view type. I'm going to do a select. This is what I want inside of this new topic. I want to make sure user ID is the key. Emit changes just means listen to everything new that's coming in, process it, and output it into a new topic. Done. Okay. I can start from the beginning, etc. Now, how do I want to use these? Let's see, I have about 10 minutes. Let's see what I could get away with. and we'll show an example of that. So let me come in over here. I probably won't be able to do the entire demo because I have about, 13 minutes left or 10 minutes left. But let's see what I could pull off on this one. So what I'm going to do on this one is maybe I'll just get done halfway on this. But what I have here is I have this one's called Connect. And what I'm going to do is kind of do a outbox pattern from this. And so one of the things I could do is I could run this one, and I think I should be ready to run this one. This one's going to post to PostgreSQL. I have a PostgreSQL database that's running. Let's see if I could just run it here. Can I? Yep, there we go. So this is posting onto a database currently. Okay. And I'm going to use something called Kafka Connect. Kafka Connect, I talked to you about that one. Kafka Connect allows me to read from a database and bring that one into Kafka. But right now, I'm just writing stocks into a database. These are the IDs that are coming in here. Now what I want to do is I want to use Connect to bring information in. So let me bring up my cheat sheet in here. And I'm going to set up this connector for ourselves here. Stand by. And here it is. So I'm going to set up a connector so that way I could start to read it. And I'll show you a little bit of a KSQL DB on that. All right, so here's the connector. So I'm reading in from a database. I'm going to go here to connect. And I'm going to add a connector. And I want to read from a JDBC source. So what I'm going to do is say convert every row from a database into Avro. Okay, that looks good. And what else am I going to do? Oh, let me change the screen. Sorry about that. Oh, no, I did already. Okay, good. Let's see. User is Docker. Here it is. The user is Docker. The password is Docker. Don't tell anyone. Super secret stuff. Here's the URL. So I want to start to read information from a JDBC source. Okay. The loading mode is incrementing, meaning in that one that I want to read the, this one's going to be Postgres. I want to read the IDs is what I want. And so that's the table loading mode. Topic prefix. Maybe. There's a lot of fields. So there's that one. And then finally over here, we're going to do additional properties here. We're going to add a property. Stand by. Okay. I'm going to add another property. This one right over here. Got about 9 minutes left. Here we go. We'll get there. And so I'm going to add these properties in here, which is the schema registry. And looks like I'll just get away with hopefully showing you a connect. So connect here is, again, just bringing it from a database into Kafka. I'm going to launch it. I hope. There we go. And running. That was nerve-wracking. All right, so it's running now. And in fact, I should see now inside of topics the something. Yeah, here it is. Postgres stock trade. And let's take a look at the messages here. This one's going to be using a schema now. And take a look at the way this looks. Beautiful. Look at that. I have ID. I have a stock symbol. I have all this in here. I have structure, and therefore I could query it. And these are messages now that I could deal with. So what can I do with this? All right, let's finish things up now with a KSQL DB. So I'm going to come in over here, and let's give this one a try. And what I'm going to do is I'm going to launch KSQL or KSQL DB. Let me go to my services here, and I'm going to open up the CLI, and I'm going to create a terminal inside of it. There it is. So I'm going to go ahead and bring this one in. There we go. And so what do I want to do with this? Well, I'm going to attach to this. I'm going to create some stock trades in here. There it is. I'm going to set this up to say, read everything from the very beginning. And I'm going to show some live data as it's coming in. So here's an example of that KSQL DB. Nice, right? You can see all that data in here. That's live. That emit changes that I'm adding here says, whenever there's something new to report it to me. I want to take a look at it. Okay. So let's try this one over here, and then I think I'll stop there. And here it is. Here's the persistent query. And what this is going to do is the following. I want to create a topic called stock count. And check this out. My origin is Avro, but in this case here, I want to convert it to JSON. And this will have the stock symbol. This will have another stock symbol. So this one here will be the key. This will be the value. And this will be the count. And we're going to get it from stock trades. And I'm going to do a group by on it. Powerful. All right, let's take a look here. Notice here, I'm not seeing any response here. That's what a persistent query will do. Okay. And if I take a look over here now, let's take a look at our topics. I have stock count. If I take a look at the messages on here, it's a different materialized view representation of that data. It's just shy right now, so it's not showing up. All right, well, there it is. Oh, here's Netflix. Okay, so Netflix has a count of 1. WBD has a count of 1. Right, so I'm aggregating information live. Now, all this is part of a CQRS. CQRS is Command Query Responsibility Segregation, where you can do a lot of things with it. And so CQRS is get from one read model, like a database, bring it in, munge it, do something with it, change it, and then post it back to another database. And so as part of this final conclusion to all this is the following, maybe. Here, let me get my slide back on here. So I have a lot more information on the slide here, but the idea for all of this is you can do stuff like this. This is called the choreograph saga. These hexagons here are your microservices. You should be able to trigger from events. That's what part of event-driven architecture is. This whole ecosystem is amazing because you can bring in messages, do something with those messages, post them to a database, read from one database over to another, consume them, right? And everything revolves around Kafka as your center backbone. Okay. And I'll go ahead and leave it right there. Okay. Again, it's part of any large architecture, and it's good to know. And if you're looking for, studying up on something to advance your career, this is a great place to do it. Okay. All right, I'll leave it at that. And thank you very much. And thanks for allowing me that full time there. It's got a lot of demos and really appreciate it. So I'll hand it back to Camille. Thank you, Camille.
Thank you so much for that wonderful presentation, Sir Daniel. So we are now opening the floor to your questions. So to our audiences here with us, you may input your questions in our Q&A chat box, or you may raise your hand so we can unmute you and you can ask your question to Sir Daniel. So you may now input your questions here. I see a lot of emojis, clapping emojis.
Yeah,
Thank you so much
I
for
I
sharing
feed
your
on these emojis,
appreciation.
so the
Yes,
emojis
sir.
are good.
All right. So, any questions for Sir Daniel? Please don't be shy. So, I know Sir Daniel won't bite you. So, he would be much more delighted if you would ask him some question for his regarding his discussion. So, you may raise your hand so we can unmute you, or you may input it in your Q&A chat box. So, do we have any questions?
Either people are
I
shy or scared. That's
yeah,
right.
probably, sir. So, I think that's it, sir. So, thank you so much once again for your discussion. So, we will now be moving forward to the program. Before we move on to our next speaker, we will be giving a short break, a short 5-minute break. You can take this break to do go to the restroom, have some snacks at your home or at your office, wherever you are joining us right now. So we will be back after 5 minutes. Thank you so much. All right, so I hope you enjoyed your short break. So we will now be moving forward to our next speaker. So our next speaker is an expert software engineer and delivery lead with over 12 years of experience in software engineering. And since joining Zulhke Singapore in 2021, he has driven success for the company and its clients, particularly in private banking. And this afternoon, he will be discussing Kafka, fundamentals, and application. So let us welcome Mr. Renz Rollon. Welcome, sir.
Hi, good afternoon, everyone. Thank you for the introduction, Camille. Let me try to share my screen. There we go. I'm hoping you could see it now. Okay, as Camille said, I'm from Zulhke, Singapore. We are also service providers or consultants like Orange and Bonds, right? If you're familiar. And one of our biggest clients is UBS. It's the largest bank in Switzerland. And it is where I gained my first-hand experience with Kafka. And that's why I'm here today, talking and presenting. Okay. Which my presentation will be short, so yeah, bear with me. I don't want to delay your weekends and mine. Since Daniel also covered most of the first part of my presentation, so I will just highlight a few slides and skip most of it. Second, I'll talk about how we use Kafka in core banking. And third, how Kafka is used in Gen AI. Then if you have questions or clarifications, we'll have a question and answer portion also. Okay. You know an event already, or you can call it a message or a record. Event streams, as discussed earlier. Some use cases or initial use cases of it was LinkedIn, tracking the user activity, Uber with their dynamic pricing, driver rider matching, and Netflix, which is ingesting data from millions of devices. I'll highlight a bit on this slide about streams and tables. I've seen Daniel use chess as an example earlier, so it looks like everyone here loves chess. Let's use it again. On the left side is a sample of a stream. It shows the history, the every move in chess that has happened. And on the right side is the table, which shows the current state of the board at any given time, or at the current time. It is important because in your projects, you need to know, depending on your use case, which one do you want? Do you want a table? Do you want to query the current state? Or do you want a stream? You want the incoming records as they go in, or the entire history of records, right? It is also important to note here that you can convert streams and tables into one another. Like if you have streams, you can perform some aggregation or aggregate operations to convert them into a table. And if you have tables, you probably have also a stream or a log in your database that we almost never touch, but it's there. There's a log of changes in your tables. So you can convert streams and tables into one another. Another example that's mentioned earlier, if a record Bob arrives, it's an insert to a table and stream. If another event, you update the table, but you just insert it to the stream, and so on and so forth. As Daniel mentioned, streams are immutable, so we always just insert. And Kafka is the de facto streaming platform if your use case is streams. Right? Daniel discussed the components of Kafka already. Basics is you have producers, you have your Kafka clusters and consumers. Zookeeper manages your cluster. I think there's a latest implementation now called KRaft. Right? Zookeeper is an external entity or component compared to KRaft, which is internal to your cluster. The APIs, Daniel also show some demo and codes. The Kafka producers and consumers, we also have the connect. I'll just add here that connect is basically the same with your producers and consumers. It's just that connect source or connect removes the boilerplate code. So it's a collection of libraries now provided by Kafka. So you can easily configure to your source databases. And the counterpart is the sync. It's also a collection of libraries. So you can easily upload to your target databases. But underlying, they're just the same with producers and consumers. Again, Kafka streams, they process your streams and do some transformation, conversion, or cleaning, and they output another stream back to the cluster. Yeah. Yeah, the topic was extensively discussed earlier already. Yeah. If you understand it fully, you'll have a different number of brokers in your cluster. Like in this example, we have 4 machines as brokers. And topic 1 has 4 partitions. It can be different per topic, right? And the replication factor is 3, meaning each topic partition is replicated to your brokers 3 times. So if one broker goes down, for example, broker 1, you still have this partition 0 in broker 2, partition 2 in broker 3, partition 3 in broker 4. Right? In our production environment, I think we use 6 brokers, and partitions is, I think, 3 or 4, and we have hundreds of topics. We normally map one table from the database to one topic, and replication factor is minimum is 3. Yep, that's it for the first part. It's already discussed heavily by Daniel earlier. I'll now move to the second part, which is Kafka in core banking. So I'm in UBS, which is a Swiss bank. I'm under core banking. We have a centralized system that manages and processes fundamental banking operations. So we use a comprehensive core banking software, T24, from Temenos. It's a complete solution for normal banking operations, right? And it also has its own database, meaning most of the transactional data in the bank is being handled by us in core banking. Other departments like rule center, risk management, portfolio services, client onboarding, etc. They need our data on a daily basis. Example of transactional data, you have stock purchases, deposit and withdrawals, loans, portfolio management, or corporate actions. So since we have a lot of data, majority of the transactional data, and other departments need it, we still don't want them to querying our database directly. Like there's a lot of disadvantage to that. Like the database design, they might not be optimized for querying, the formatting of the data. You don't want everyone to convert them on their own. And so we prefer to encapsulate the data, and that's what we do in core banking. We provide APIs to serve the data to external systems in the external teams. So every data must flow in our APIs. There's no direct querying in the database. And that's why we have Kafka to expose real-time data in our APIs. There are two types of data in the banks. Like there's intraday and there's end of day. Intraday example, there's cash flows, settlements, payments, dashboards. So your use cases for this, you need the data immediately or the transaction immediately as it comes. Maybe for alerts also. It's critical for the systems to receive them as soon as possible. And there's also a use case for end of day, use cases for end of day. Like if you need reconciliations or reports, fulfill some compliance, generate statements, or sometimes you need snapshots of your data for each given date. So the left side is where we need a streaming platform. That's why we created Kafka for it to serve the data real time as we received it in core banking. Okay. Just copying our architecture here. It doesn't make much sense. Actually, like there's too much jargon and banking internal terminologies. So let me convert it and relate it to the Kafka APIs from earlier. There you go. If you see from the left side, the T24 that I mentioned earlier, we have an Oracle databases there, right? That's the source of our data. Oracle database has this event logs. It tracks the changes in the databases. So you might have some type of this event logs also in your normal database. It's just that we rarely query them. We rarely have use cases for them. But if you want to stream your data, you need this specialized tables or logs to retrieve the changes. Like you don't want to query all your tables just to detect the changes every time. And we have this application here. It's actually just a source connector. So it contains library for Oracle that's easy to retrieve the data. What it does is there's some polling interval, like maybe every 10 seconds or every 30 seconds, we run some query to this event logs to detect the changes that happened in all of the databases, right? And we push them to our topics, the initial topics. And yeah, there are several stream processors using those push topics. There's some conversions happening, renaming of the fields, maybe cleaning, some transformations, right? So for each tables in D24, there's hundreds of it. We create the topics, and then these stream processors do some transformations in all of those topics, right? You see here, the naming of the topics change as the stream processor processes them. Like one stream processor will listen to a topic and do some processing and upload to the next topic. And this is our Kafka cluster. Then we have the final topic here, in which the consumers can already consume. They can subscribe to it if they want a subscription-based implementation. Or most consumers also want an API base, like you just want to query our API. So we also need to create and provide the APIs for them. Wherein we use a connector again, this time a sync one, a sync. We put it to another database like an Elasticsearch or MongoDB that is more efficient in serving APIs or queries, right? Because these topics are not really efficient when querying. Okay. So again, we use Oracle databases, and there's a source connect to pull the changes in the tables and upload it to a topic. Then there are some same processors that do something with your data before it goes to the final topic, which consumers can already subscribe to. If your consumers need APIs, then we need another database to sync those data to and make it queryable. Okay, the challenges that we've encountered. First is a change data capture. For example, in the Oracle earlier, these various event logs and actual events, it might not be there, or it might not be in the format that you're expecting. So it's a challenge if you have an existing database already, but there's no clear change data capture implementation. Right? It's difficult how to detect the incoming changes or the changes that happened in your databases. Most database solutions have these logs. They do log for Oracle MySQL, transaction log for SQL Server, and write ahead log for Postgres. Although sometimes you'll encounter existing database that really complex to implement this. The next one I've mentioned earlier is querying our data from the topics. It's you can probably do it a straightforward way, but it's not efficient. So you need to sync it or dump your data first to a more efficient database like Couchbase, MongoDB, or Elasticsearch. And now you can expose this to your APIs. Okay. Why is it a challenge? Because there's another layer for your data. You might need to duplicate everything, and you need to maintain the consistency, right? Another one is managing the cluster. For example, we have hundreds of topics. It's difficult to manage it as a team. Someone should always be familiar with the configuration and Kafka, right? There's always operational overhead. So what we're doing right now is we started to migrate to Confluent Cloud, which is the Kafka as a service, and it will solve most of this problem. But yeah, it will cost way more as we're planning it. The first one we're using is an open source Kafka, and yeah, the cost is way higher. Okay. Yeah, that's it for use case of Kafka in the bank. I can now move to Gen AI. Everything wants to integrate with Gen AI nowadays, so let's tackle also how Kafka does it. Our example here is we have a chatbot or flight assistance, right? Like your chat GPT. but it looks like it's asking for some specific or context knowledge. So on software like this or applications like this, the data should be fresh. It, it should also like it's updated, up to date. You don't want your chatbot giving you data from 5 years ago or 10 years ago. It should also be domain specific or contextualized, like should know the policies of this airline, right? You don't want to receive some generic policies for all airlines. And it is trustworthy, like it is accurate. We don't have any Gen AI projects yet in the bank. So most of these following slides are just from my personal reading. And yeah, who's familiar with RAG applications already? It's retrieval augmented generation. It's a technique to handle the data requirements I've mentioned. It should be fresh, domain specific, and trustworthy. So other than your normal LLM answering your queries or prompts, RAG allows you to query first your vector store so that you can get the relevant context. For example, the flight or the airline details, airline policies, and add it to the prompt before calling your LLM. Okay. To how this vector store is populated in RAG. Usually you have additional data, you chunk them, you have an embedding model so that you can perform mathematical operations and save it to your vector store. Because LLM, if you don't do this, you might need to retrain your LLM, which is more costly, right? So it's better to append another database or a vector store. So you'll have a updated and with context response. Okay. Kafka can be useful, or data streaming in general can be useful in RAG applications. Data augmentation, this is preparing your data in your vector store. Like before you can query something on it, then you need to populate it with data first, right? Like ingestion or augmentation. And how Kafka or streaming is used is we have our source data, maybe some documents or policies or just an external data that's relevant to your business. We use source connectors and upload it to our cluster or topics, right? We use Apache Flink. Daniel mentioned it earlier also. It acts like a stream processor in Kafka. You do something with your data, you vectorize them, or you transform it to embeddings, right? With the help of an embedding model. And now you can uh, save it to your vector store. Okay. This is helpful, especially if you have several vector stores in the organization and your Kafka stream can all coordinate or integrate in populating the corresponding vector stores. If it detects that this data may be important to this vector store, for example, about sales or stocks, right? You can populate your vector stores with your streams. Another look at it, right? You have a data store, source connector, an example topic here, customer service logs, then some stream processor using Flink. We do the embeddings and we sync it to our vector store, like MongoDB, Elasticsearch, and so on. So we now have a ready vector store for a RAG application with the help of Kafka. We now look into how the inference is done. Like if some users submit a query or a prompt, like how Kafka can help on that. So for example, you submit a query from your web application. You can now stream it in your cluster instead of calling your LLM, instead of this, right? Instead of just querying vector store and calling LLM, you now send it to your cluster first and process the stream using Flink, embed it, and save it to your vector store. So the advantage now is for all your user prompts, you're enriching or augmenting the data also in your vector store. You're updating it, right, with the latest data. And yep, you'll also call the LLM here. It will send a response. The response will, you can also enrich your vector store with the response from the LLM, right? And it will, you know, return back to the web application, to the user. Yep. Here's another look for inference. The chatbot web app, the user sends a prompt. It sends to Kafka, then Flink SQL. There's some operation like ML predict native to Flink to call the LLM, like the Flink do your embedding so for yourself. And yeah, we enrich the vector store with the inference from LLM and the prompt from the user. So our vector store is always updated and the context also, or the domain specific data is updated in the vector store. So the response to the user should be more updated now. Okay. And again, if you have multiple web apps, multiple chatbot, like you can combine all your Kafka cluster streams, SQL, such that each one is helping uh, each application's vector store. They're populating one another. Okay, so maybe the domain specific prompt from your airline chatbot web app can contribute to the sales chatbot web app, right? Or transportation chatbot web app. Okay, so that's how Kafka streams comes into RAG applications. And yeah, that's all for me. Any
Thank you.
questions?
We have an attendee raising his hand. So,
Oh, Jenna. Okay.
hello. Hello, Jeno. You may now ask your question to Sir Renz. We have unmute you. Jeno, you may now unmute yourself and ask your question. Or you may also input your question in our Q&A chat box. Jeno, are you there? One last call. Hi, Jeno. I don't think you will proceed with this question. So, any more other questions for Sir Renz here? To our participants, again, you may input your questions in our Q&A chat box, or you may raise your hand so we can unmute you and you can ask your question directly to our speaker. So, please don't be afraid to ask questions. So our speaker would love it if you would share your questions with them or your insights. You may also share your insights or what you think about the topic. So please don't be shy. So another call for Jeno. So we have already unmute you. If you want to ask your question, you may now unmute yourself. Mm-hmm. All right, so sir, I think that's it. So thank you once again to our speakers, Sir Daniel and Sir Renz, so for joining us today and for sharing your insights and expertise to our audiences. And thank you to our audiences who joined us today. We hope you learned a lot from our speakers. So again, let me just share my screen. So we will be sharing a Q&A, a feedback form. So please keep in mind that we will be sharing the certificate of participation to you once you accomplish the feedback form. So we will also be sending our speakers deck to you once you have accomplished the feedback form. So you may access the feedback form here in our QR code. So you may take a screenshot or scan the QR code here in front of you. All right, so moving on. So we'd also like to announce that we have our next enablement seminar series. So for April, please expect employment training. So we will be sharing with you the marketing posters soon. So please stay tuned to our marketing. So we'll be sending some emails and uh, we will be posting the marketing poster on our Facebook pages and our LinkedIn page. So stay tuned for that. So for me, we'll be having ethical and responsible AI. So for June, we'll be having agile anti-patterns. For July, we'll be having AI and ML use cases. For August, we'll be having testing best practices. And for September, we'll be having dataset-driven AI systems. And last but not the least, for November, it will be introduction to microservice development. So we hope you look forward to these enablement seminars and we hope you'll join us also. So once again, thank you so much. So we hope you look forward to our next session in April and we hope to see you there. Thank you so much once again to our speakers and to our audiences. You may now exit the Zoom. Thank you so much.